Okay, hello everyone. Let us continue the first part of today's class. Okay, in the third part, we have talked about the theorems and properties. If the determinant of any identity matrix is 1, G, let A and B denote any two matrices having the same dimensions n by n, and A denote any non-zero scalar. Then 1 over A to the power of n times the determinant of A plus B is equal to the determinant of capital A over small a plus capital B over small a. H, the inverse of any n by n matrix A exists if and only if: first, R of A is equal to n, that is, A is full rank, and second, the determinant of A is not equal to 0. I, for any square matrix A, it follows that A inverse Hermitian is equal to A Hermitian inverse. J, for any normalized unitary matrix U, the determinant of U is equal to 1. K, let A denote an n by n matrix, then 1. A necessary condition for A times A Hermitian inverse to exist is that n is greater than or equal to m. And second, a necessary condition for A Hermitian times A inverse to exist is that m is greater than or equal to n. L, for any square matrices A and B, it follows that the determinant of A times B is equal to the determinant of A times the determinant of B. M, for any square real matrix A, the determinant of A transpose is equal to the determinant of A. N, for any square complex matrix A, the determinant of A Hermitian is equal to the determinant of A star. O, for any matrix A times A Hermitian and A Hermitian times A are Hermitian. P, let A be an n by n matrix with eigenvalues lambda I. Then the determinant and the trace of A can be expressed as follows. The determinant of A is equal to the product from I is equal to 1 to n lambda I. Okay, that is, the determinant of a matrix is equal to the product of all of the matrix. Is equal to the product of all the eigenvalues of the matrix. Second, trace of A is equal to summation I is equal to 1 to n lambda I. That is, the trace of A is equal to the sum of all the eigenvalues of the matrix. Q, any square matrix is singular if and only if it has one or more eigenvalues equal to 0. R, singular value decomposition. For any complex n by n matrix A of rank R, there are unitary matrices U, which is an n by n matrix, and V, which is an n by n matrix, and a diagonal matrix D, which is an R by R matrix, which is equal to the diagonal matrix sigma 1, sigma 1, sigma 2, etc. to sigma R. Okay, this notation denotes that this is a diagonal matrix with the diagonal elements equal to sigma 1, sigma 2 to sigma R, and the other elements are all equal to 0, such that A is equal to U m by m, D0, 0, 0, Vn by n Hermitian. Okay, so you can know that these 3 zeros are matrix. Okay, because we need to multiply these 3 matrices together, so the number of rows of this matrix is equal to m. Okay, so the number of rows of this 0 matrix is equal to m minus r. And because we can multiply this matrix by this matrix, so this matrix has n columns, and the number of columns of this matrix is equal to n minus r. Okay, with sigma 1 is greater than or equal to sigma 2 is greater than or equal to etc. is greater than or equal to sigma r, where sigma I are called the singular values of A. Let A be any complex matrix and denote the singular values of A by sigma I, and the eigenvalues of A times A Hermitian and A Hermitian times A by lambda I. So do the eigenvalues of A times A Hermitian and A Hermitian times A equal? Okay, let us see the handout. Okay, page 238, problem 1. Let A be any complex matrix. Do A times A Hermitian and A Hermitian times A have the same eigenvalues? If your answer is yes, please prove it. If your answer is no, please give a counterexample. Write down the correct statement and prove it. Answer left to you as an exercise. Okay. Then sigma I is equal to the square root of lambda I, where I is equal to 1, etc. to R of A times A Hermitian. T, for any Hermitian matrix A with eigenvalues lambda 1, lambda 2 to lambda R, the non-zero singular values of A, sigma 1, sigma 2 to sigma R are given by sigma I is equal to the absolute value of lambda I, where I is equal to 1 to the rank of A. U, eigenvalue decomposition. Suppose that A is a Hermitian matrix of dimension m by m and rank R. It follows that there is an m by m diagonal matrix D, of which the size is m times n, is equal to a diagonal matrix, and the diagonal elements of this matrix is equal to lambda 1, lambda 2 to lambda r, and 0, where r is smaller than or equal to m. So you can know that there are m minus r zeros here. And a normalized unitary matrix U dimensioned m by m such that A is equal to U times D times U Hermitian, where lambda I are the eigenvalues of A and R is equal to the rank of the matrix A. In this case, the columns of U are the eigenvectors associated with the eigenvalues in D. Okay, the columns of U are the eigenvectors associated with the eigenvalues lambda I in D. VQR factorization. For any m by n matrix A, it is possible to express it as a product of two matrices as follows. A is equal to Q times R, where Q is an m by m unitary matrix and R is an m by n upper triangular matrix. Okay, what is an upper triangular matrix? Okay, please see the handout. Page 241. A matrix is called upper triangular if all the entries below the main diagonal are 0. For example, A is equal to 1, 2, 3, 0, 4, 5, 0, 0, 6 is an upper triangular matrix. Note, there are various versions of this theorem. The one used above matches the MATLAB convention. Okay, what is the meaning of convention? Okay, it means 惯例、习俗、常规。W Rank plus nullity theorem. Consider an m by n matrix A. If m is greater than or equal to n, then R of A, that is the rank of A, plus the dimension of n of A, that is the null space of A, is equal to m. If n is greater than or equal to m, then the rank of A plus the dimension of the null space of A is equal to n, where dimension of the null space of A, which denotes the dimension of the null space of A, is equal to the minimum number of basis vectors needed to span the null space of A. X, let A be an m by n complex matrix and consider the m by m Hermitian matrix A times A Hermitian with eigenvalues lambda 1, lambda 2 to lambda r, where R is equal to the rank of A times A Hermitian. It follows from the definitions of trace and Frobenius known in section 1.9.2p. Okay, let us see the section 1.9.2p. Okay, this is the section 1.9.2p. Let A be an n by n matrix with eigenvalues lambda I. Then the determinant and trace of A can be expressed as follows. The determinant of A is equal to the product of lambda I is equal to 1 to n, and the trace of A is equal to summation lambda I is equal to 1 to n. Okay, that the trace of A times A Hermitian is equal to the summation I is equal to 1 to R lambda I, and is equal to the Frobenius known square of A. Okay, why let A and B denote two matrices that are dimensioned m by n and n by m respectively. It follows that partial of the trace of A times B over partial A is equal to B transpose, and partial trace of A times B partial B is equal to A transpose. Okay, how to prove this equality? Okay, please see the handout. Okay, page 244. Problem 1. Let A and B denote two matrices that are dimensioned m by n and n by m respectively. Show that partial of trace of A times B over partial A is equal to B transpose. Okay, this is the answer. The derivative of a scalar y with respect to a P by Q matrix X is given by partial y over partial x is equal to partial y over partial x1 1, etc. to partial y over partial x1 q, and so on. Partial y over partial xp1, etc. to the partial y over partial xpq. Okay, now we let A is equal to A11 to A1n and so on to AM1 to AMn, and matrix B is equal to B11 to B1m and so on to the Bn1 to Bnm. Then the product of A and B is equal to A times B. Okay, A times B is equal to summation I is equal to 1 to n A1I times BI1. Okay, how do we get this equation, this term? Okay, you just need to times the first row of A to the first column of the matrix B term by term and add them all together. So it is equal to A11 times B11 plus etc. plus A1n to Bn1. Okay, so it is equal to A1I times BI1, and I is equal to 1 to n, and make the summation. So similarly, the last element of the first row of AB is equal to summation I is equal to 1 to n A1I times BIM, and the first element of the last row of the matrix A times B is equal to summation I is equal to 1 to n AMI times BI1. Okay, and so on. And the final term is equal to summation I is equal to 1 to n AMI BIM. Okay, if you is not familiar with this notation, okay, you can do the conventional the multiplication of matrix A and B turn by turn, and try to represent them into the summation form. Okay, please do it by yourself when you go home. Okay, the trace of the matrix AB is, okay, trace of A times B is equal to the summation J is equal to 1 to M, and A times B JJ, that is the summation of all the diagonal elements of the matrix A times B. Okay, and note that the dimension of the matrix A times B is M by M. So there are M diagonal elements. Okay, so it is equal to the summation of this term and so on to this term. Okay, so it is equal to first A1I times BI1 to AMI times BIM. So we can write this as AJI times BIJ, okay, where I is equal to 1 to N, okay, because this I is equal to 1 to N, and here is also I is equal to 1 to N, and finally the outer summation is summation J is equal to 1 to M. Okay, because here is the J and here is the J. Okay, so J is begin from 1, and finally J is equal to M. Okay, here and here. Okay, the PQ's element of partial of trace of A times B over partial A is equal to partial over partial APQ. Okay, and the trace of A times B, we can substituting this term into here. Okay, copy this term to here. Okay, then the partial can be moved inside of the summation. So this equation is equal to the summation J is equal to 1 to M, and summation I is equal to 1 to N. Partial AJI times BIJ and partial APQ. Okay, we know that the partial derivative is equal to BQP. Okay, why? Because the partial APQ times BQP over partial APQ is equal to BQP, and for the other terms, okay, the AJI partial AJI BIJ over partial APQ is equal to 0. Okay, so this is equal to BQP. Okay, here for P is equal to 1 to M and Q is equal to 1 to N. Okay, therefore partial of trace of A times B over partial A and its PQ's element is equal to BQP. Okay, so this implies that partial trace of A times B over partial A is equal to B transpose. Okay, this completes the proof. Okay, let us go back to the slides. Okay, Z. Let A be a square matrix dimensioned M by M and I be the identity matrix with the same dimensions as A. Okay, it is 25 minutes now. Okay, so see you next time. Goodbye.